Okay, welcome everybody to the webinar. My name is Jennifer Griffith, and I work at NMOA, which is the Northeast Waste Management Officials Association. We are an interstate association of the 6 New England states, New York and New Jersey. We're the waste programs, the solid waste and hazardous waste programs, also the toxic use reduction programs, and then also the waste site cleanup programs in the states. And for the past, since about 2016, we have had a strong focus on PFAS ever since some pretty high political sites emerged in New York and Vermont and New Hampshire. So this is part of the sort of education and training that NMOA and information sharing that NMOA provides for its members, and then we also open up our events to the consulting community and others, and then these webinars are open to folks all across the whole world, I guess. So this webinar, we've got a lot of people registered that will be joining us from all over the country, including some folks that got up very, very early or maybe haven't gone to bed yet in Guam. So welcome everybody to this webinar. So I just want to let everybody know this is what NMOA is. This is our website, and I just have it up here to sort of show people where the presentations will be posted following the webinar, well, like tomorrow or Monday. So you click on Waste Site Cleanup, and then you go to Events, and then here's all the upcoming events we have, and this will become a past event, and then they're in chronological order going backwards, so you have to find them. But we have a bunch of things we've done in the past, a lot of different webinars and workshops. The presentations from all of them are posted. If you're interested in any of these topics, you're welcome to check out the presentations. And then I just want to make sure everybody knows we've got this is the one we're doing today, but we've got 3 more that are scheduled on the books. Next week coming up is focus on landfills. New York and Vermont have done some investigations and some studies, so they'll be presenting those. June 23rd, we'll be talking more about lessons learned with field sampling and some cross-contamination issues, including Alpha Analytical did a study that they published some results of that you may have seen, where they looked at different equipment and other supplies that people use in the field and tried to do some analysis on them to see where which ones contain PFAS and might be contributing cross-contamination or not. So that's interesting. And then on July 8th, New Hampshire and New Jersey have been doing a lot of work, and will be presenting sort of a summary of their work, including trying to look at forensics and sources and identifying sources of PFAS. So hopefully you all can register for those as well. So with that, I will go back to homepage. So today's webinar, since we have so many people joining us, we will not be taking questions verbally. Everybody will stay muted, and you should type in your questions at any point. And then when the presenter is finished, I will look at the questions and ask hopefully all of them, but at least some of them, to the presenter. We'll do the first presentation, have a few questions, and then we'll do the second presentation and follow up with some questions. So that is the logistics for this. So with that, I'm going to turn over the screen to our first presenter, who is Steve LaRosa. He is the team leader and a senior project manager at Weston and Sampson. He's in their Waterbury, Vermont office, and he's currently the manager of all the PFAS-related projects at Weston and Sampson. He's got over 30 years of experience in the field of environmental assessment and cleanup. He's the leading member of their emerging contaminants work group, and also is a member of the ITRC PFAS training subgroup. He's designed and overseen the implementation of sampling and evaluation of PFAS sources and impacts in many sites in Vermont, Rhode Island, Connecticut, and New Hampshire. He's also led a comprehensive assessment of PFAS in wastewater, biosolids, land application sites, landfill leachate, and surface waters. So he's going to be presenting today sort of an overall picture of PFAS fate and transport. So with that, take it away, Steve.
Great, thank you very much, Jennifer. I appreciate it. So today, I'm going to try and lay some of the groundwork for understanding some of the mechanisms and reasons why PFAS compounds are a little bit unique in the environment and how they move and what their fate and transport are. We have assumed in our presentations here that folks who are joining the webinar have some basic knowledge of what PFAS are and why they're a concern. So I'm not going to delve a bunch into the types of products or the history of use and those things. There's some great resources out there, and at the end of my presentation, I've got some websites that if you really want to dig deep into to anything I talk about or into PFAS in general, there'll be great places to go. But basically, I just want to go over some of the high points of what makes the PFAS compounds unique in our environment. I think that everybody's heard them called in the news and those things forever chemicals and chemicals that that won't go away. So that's kind of one of the themes here. But basically, in order to understand the fate and transport, you need to essentially develop a conceptual site model or an idea of what are the where, when, how kinds of questions that need to be answered to really be able to understand where these compounds may have gone and where you need to look for any impacts. So to that end, release mechanisms are really important. What kind of source material you have. PFAS are between 3,000 and 7,000 individual compounds, and they were used for a lot of different materials out there, from firefighting foams to carpet protectors, coatings for wiring, waterproofing for clothing. There's lots of different uses, which brought about lots of different formulas. So there isn't really a kind of, one compound fits this mechanism and this release, and another fits a different one. You've got a real soup out there of what you may have. The structural makeup really is important for looking at fate and transport. And then that really leads into the last bullet here, which is the partitioning. Where do these compounds stick? Where do they not stick? What kinds of phases do they want to be in? Are they going to be vapor phase? Will they be solids? Those kinds of things. So to kind of give you an overview of the different places and things that PFAS can impact is this great slide here from the American Waterworks Association. And they really show kind of all the potential sources and potential cycling or recycling of PFAS through the environment. In the upper left is the obvious big one that everyone likes to jump a hold of, which is industry. And maybe they make or they use PFAS, and the PFAS can actually be discharged through stack emissions. They may go out in the wastewaters or process waters out into streams or wastewater treatment facilities. And then you have the products themselves, which may end up in the center of the screen in your home. where they're being used, and then they end up going maybe to the landfill when they're done being used. And the unique thing about these compounds is they are used as waterproofing and chemical resistance, but they're very soluble in water, a lot of them, and they can migrate very easily, and they don't like to stick to soil. So you may see releases from landfills, or if you have on-site wastewater systems, you may see it there. If the PFAS get into the drinking water, then that can also lead to impacts in your house and to treatment of that drinking water that may yield some additional compounds. And then all the way up in the top of this slide is one of the major sources of PFAS that you see surrounding airports and oftentimes Department of Defense sites, which is firefighting foam. So PFAS are a key component in the foams that are used to fight fires at airports and with unique solvents, and you can see quite a bit of a release from those. So release mechanisms and uses are really important. You can have releases, as I said, to the air from stack emissions, and there's some evidence that you may see it from the releases from AFFF responses. The PFAS will be transported in air and can potentially impact very, very large areas. Surface soils, they will be impacted by runoff or by air deposition, potentially by dumping. Surface water can be impacted, groundwater, sediment, and then biota, which are the plants, animals, and people who ingest contaminated materials or air as you go about your life. So these release mechanisms obviously are very wide ranging and hit essentially every environmental media that is out there. So again, source type, AFFF, the firefighting foams, they are less than 5% PFAS. However, you use a fair degree of these at a source site, and they're a pretty complex mixture. So that complexity of the PFAS and the hydrocarbons or the fuels that are being put out in a fire, coupled with any other releases that may be occurring at a catastrophic incident, makes for a very, very complex chemical mixture that may impact the migration and concentration of the PFAS portion of what's been released. Manufacturing sources, these, for the most part, we have found are less complex. Typically, a specific suite of PFAS were utilized in order to assist in the manufacturing process. Although there are some processes out there that weren't quite as selective and used some complex mixtures. Landfill leachate, a lot of old closed landfills, particularly here in the Northeast, aren't lined, and they may have leachate that goes through them that can get directly into surface water or groundwater. And that can be a very complex mixture to deal with, as you can imagine, with all of these different consumer products mixed together. And then the final one I have here is wastewater treatment facilities. And you'll hear a little bit about the wastewater treatment facilities in the second presentation today, but there's lots of inputs, obviously. Unfortunately, wastewater treatment facilities don't really fully treat or oxidize PFAS. So they kind of pass right through them. And therefore, you can have PFAS in the discharge to surface waters. You can have PFAS in the biosolids and sludges that are generated. And that makes for a very complicated mixture again with these sources. So structural makeup of the compounds. This is what really makes, again, the PFAS very complicated from a fate and transport conceptual model. Not only may you have a bunch of these types of compounds from the various sources we talked about, but the structural makeup of these makes them very unique. They're anionic perfluorinated alkyl acids is what we're talking about in this slide. So the PFOA or PFOS that are shown on the left are these perfluorinated, so fully fluorinated compounds with that fully fluorinated tail on the left and some sort of active group or anionic head on the right. And what that does is it makes these compounds negatively charged. They don't have much vapor pressure, so they don't really put themselves into the vapor phase. Although, as I said before, you can see these coming out of a stack as part of a process at a facility, but they aren't actually vapors. And they're very water soluble. They're surfactants. And so they like to orient themselves with their anionic head in the water and their non-ionic tail up in the air. And that, again, for the second discussion today, you're going to see how this can be very, very important in the migration of these compounds through soils and those things. So you look at the anionic perfluoroalkyl acids as a whole, and that's really what we're dealing with from a regulatory standpoint. Again, for the most part, the sulfonic acids tend to be more strongly absorbed than carboxylic acids. So again, if we go back one slide, the PFOA is a carboxylic acid, and the PFOS is a sulfonic acid. And then sorption generally increases with a higher number of carbons in your chain for that tail. And the retardation factors can be pretty well predicted. But as you can see in the table to the right, sometimes the smaller compounds have a higher retardation factor, that column all the way on the right, than longer chain compounds. You can see that in those first 5 or 6 compounds that the one with 4 carbons has a higher retardation factor than 5, 6, and 7 carbon chain lengths. So again, these are kind of some general rules associated with these, but it really comes down to the structural makeup. Now, in addition to the perfluorinated or fully fluorinated compounds, I'm sure you've heard of polyfluorinated substances. These, like the one on the left, don't have all of the carbons occupied by fluorine molecules. Excuse me. Now, these compounds are sometimes made intentionally or maybe a manufacturing byproduct when the perfluorinated compounds are being made. They have multiple states of ionic charge. They absorb to soils based on their ionic charges much more significantly than a lot of compounds do. And these can be transformed into perfluorinated compounds. So these, they're called precursors a lot of the times. They will oxidize down to or be biodegraded at times from this polyfluorinated substance to a perfluorinated end product, which these perfluorinated compounds are the quote forever compounds that we've heard about. So that is really important when we start thinking about sources, fate, and transport. So the precursor transformation, there's two different types of methods that were used to make PFAS. And I'm not going to get into the gory chemistry of this, which I know disappoints a lot of you, that you really wanted a post-lunch chemistry lesson, but I'm not going to do that to you today. But with these particular manufacturing techniques, you end up with different types of precursors that can end up making different types of end products. For the ECF methodology of making PFAS, the primary terminal end product are sulfonic acids, but you may get some carboxylic acids. The fluorotelmer method of making PFAS yielded precursors that break down only to carboxylic acids as end products. So again, knowing your source, knowing when or where these compounds may have been used and released will help you understand a little bit about this mixture that you end up with in your groundwater or in the soil at a particular site you're investigating. So with all these different chemistries and the different precursors and polyfluorinateds, et cetera, what should you expect where? If you're just getting into looking at PFAS, where are you really going to see what? So typically plumes of these compounds are very complex, and what you find where really has to do with the time since there was a release and where you are relative to that source zone. Source zones tend to be complex. They have lots of different families of compounds, particularly if you're at a firefighting location, and you may have minimal precursor breakdown. As you get into a transition zone, you see the different absorptive capacities of these compounds on soils start to separate them. So the ones that stick the least tend to be out at the front of the plume. For folks who are familiar with petroleum-related plume generation, think MTBE, think dioxane, things that are out in front of the rest of the suite of compounds you're looking at. And as you get farther and farther away, you get to the distal area where the chemistry becomes simpler just because of this filtration that's happening, and you likely end up with more terminal end products, more of those poly precursors turned into the terminal end products. So now that we've got some sense of the complexity of things that are going on here, what types of sources and transport can you expect? So transport in air, although PFAS are not necessarily volatile as a class, there are some precursor alcohols, some of these polyfluorinated compounds, that can be volatilized. But for the most part, these compounds are quote, carried as being partially dissolved or like the picture showed earlier, the head of the molecule stuck into a water droplet or in the water vapor. They can also be carried on or as a particulate. Lots of these compounds are very, very large, and they may end up essentially sticking to the particulates that come out of the stacks, and then you get your typical atmospheric discharge, both wet and dry deposition. And we've seen that these compounds can be transported miles from their source. This is a map of North Bennington and Bennington, Vermont, where there is a fabric treatment facility that Saint-Gobain ended up purchasing. And if you look at this is a typical GIS map that an environmental person would put together. Red dots are very bad, highly contaminated. Blue are good and clean. And you can see between the various facilities that operated, a landfill that's nearby, and the wastewater treatment facility that you've got orange and yellow dots of impact left to right and north to south in a giant square. Those impacts are basically 5 miles by 5 miles, so 25 square miles of impact from a facility that was less than 100,000 square feet worth of operating space. So a very extensive deposition, and all those dots are actually drinking water supplies. They're all private water supplies. They vary from sand and gravel wells to bedrock wells. So transport in the vadosome. Again, this is chain length dependent, organic content dependent. PFAS will absorb to organic carbon. They also, depending on their ionic state, like to stick to high organic charged soils like clays. So you will have, if you have deposition onto the soils or discharge onto the soils that are dry, migration occurs with recharge water, and you'll get some advective transport through infiltration. But that can be very complicated, and I'm going to leave it up to the folks from Arcadis to really get into that later. The adsorbed PFAS can act as a source of contamination to groundwater for decades. We have lots of data that indicates a, quote, non-detect reading in soils can result in leaching of PFAS at levels that you can detect in groundwater. So there's definitely low levels can result in issues further on down the line, so that source can be there for a long time. The air-water interface and the surfactant capabilities are very important if you have a petroleum release or if you have a very dry vadosome. Transport in groundwater, again, chain length and organic content is going to really drive how quickly these compounds move. However, these compounds do not absorb strongly to carbon or to soils, and they will travel vast distances in the dissolved phase in groundwater. Again, think, what you're familiar with petroleum type compounds, with chlorinated solvents. So in kind of the last few slides here, I really wanted to discuss this whole concept of forever non-degrading compounds with their mildly bound to organic carbon and soils and ubiquitous nature out there in environmental media, or at least as you saw all of those different potential sources. How the recycling of these compounds through our environment can confound developing your conceptual site model and understanding fate and transport. So I'm back to one of our original slides with all of these, as you understand now, potential sources and recycling sources or secondary sources available in the environment. And I just want to walk you through kind of one scenario of how these PFAS compounds can be released from a source and end up in many, many different areas and cause many, many different plumes or confounding data for somebody who's looking at fate, transport, and trying to figure out source and remediation, all of those good things. So I'm going to start with just a very simple diagram and go through the last few slides here. So we're going to start with industry. They're red because they're folks who are using or generating PFAS. They're a source. And then surrounding this, we've got, below them, we've got your house. And surrounding that, we have a wastewater treatment facility, so sewage treatment plant in the upper left, soil, groundwater, and surface water, true environmental receptors down below, your water supply, be it your drinking water well or a municipal water supply, and the landfill. And those are all blue because as of right now, they don't have any PFAS. They aren't being impacted. So let's have our industry make a product. So in their process of making a product, you have air that's coming out the stacks that has PFAS. You've got waste products that may be manufacturing waters. It might be just off-spec product. They go to the landfill. Then you have a NIPD's permit. They discharge some contaminated water to the surface waters near their plant, but they've got a permit for it, and it's very low levels. And then you have the actual product, and you buy that product and bring it to your house. So as you can see, in just that one step of making a product, we now have 4 areas that have PFAS within them. So now that it's at your house and at the landfill on soil, what happens? Well, that's the green arrows. You have migration through the soil and into the groundwater. Again, these are not sticky compounds. They aren't PCBs that will just stick to the soil and won't dissolve in groundwater. When you have these products at your house, let's say you have carpet at your house. Some of the dusts and those things that come off that carpet will end up in your bloodstream, and you end up excreting those. Those go to the wastewater treatment facility. You get done with the carpet, and that goes to the landfill. Well, the leachate in the landfill will typically, at least up where I am here in the Northeast, that'll end up at the wastewater treatment facility. So now we've got some additional areas that have been impacted and have products that have PFAS that act as sources, like at the landfill. If we go one step further, the blue lines are showing how when the leachate goes to the wastewater treatment facility, it gets treated, and when your effluent goes to the wastewater treatment facility, it gets discharged to the surface water because these compounds don't get broken down on a wastewater treatment plant, but they do get absorbed to the sludges and biosolids. Well, a lot of times the sludges may go back to the landfill, where they end up leaching some of their PFAS mass back into the leachate and back to the wastewater treatment facility. The discharge from the wastewater treatment facility heads to the surface waters. The biosolids, so if you've got a treatment facility that makes dried sludges into biosolids, they are fantastic for nurturing growth on farms. And maybe you have a facility that makes compost that you can use at your house. Those materials will have elevated levels of PFAS in them because the PFAS is going into those wastewater treatment plants. So that may even come back to your house. And lastly, we see groundwater migrating to the water supply, which could be a bedrock water supply, or into the surface water, and the surface water being a supply. So now everything's purple and red. We've got the water supply, if it's your drinking water well, may be recycling those PFAS right into your house. Think of the Bennington map that I showed you. All those 400 private wells were recycling PFAS that had fallen to the surface of the ground, migrated through to the groundwater, into the water supply, into the houses, which is into the people, and then out to the wastewater treatment facility. So you're getting an idea of kind of how complex this may be. And what we see is if the water supply is, say, a municipal system, they may be treating the water, removing the PFAS, and at that time, those wastes that they generate where they absorb the PFAS may end up going to the landfill. And lastly, I just kind of throw in this one on-site septic system. There are lots of states and lots of areas where your effluent doesn't go to a wastewater treatment plant, and so your wastewater may go straight to the soil and groundwater. So in summary, the important concepts are the source zones can be very complex and have long-term potential to be source zones. Investigation areas may end up being larger than you're used to, particularly if you're looking at something that may have been an airborne discharge. Perfluorinated PFAS, those are those terminal, don't break down compounds, fully fluorinated. They're still mobile. Organic carbon, pH, inorganic cations, all those things may change their mobility some, but they're still very mobile, and you may need to look for them. You'll see them dominate lots of times at the edge of plumes. The polyfluorinated precursors, you'll see a lot of them near source areas. And although I didn't touch on it here, you may be making more perfluorinated PFAS, terminal end compounds, if you're remediating in a source zone using air sparging or chemical oxidation. You may actually be transforming those compounds. And then finally, the surfactant properties in the source area, they may lead to some very interesting phenomena right in that source area with the air-water interface, and if you have any product there. So all of these concepts, all of these issues have to be kept in mind when thinking about fate and transport and looking at how your various PFASs are present in the environment. Here are some important websites. Obviously, the most important is the one on top, the NUMOA, but also ITRC has some great fact sheets. They really are a fantastic clearinghouse. If you want to get into that chemistry and some of those other things, that's a great place to go. EPA has a website, and Northeastern University does a great job. So with that, I know we kind of flew through a lot of concepts there, but that's my presentation. And I don't know, Jennifer, will we be taking questions now, or are we thinking at the very end?
Great. Well, thank you, Steve. And we do have a couple questions, also just some comments and a couple things that I can address quickly. So one is, yes, the presentation will be posted on the NUMOA website within either tomorrow or by Monday. I'll try to send an email out to everybody that attended, letting you know about that with a direct link, or you could just navigate to it through the NUMOA website. The vadose zone is the soil that's between the groundwater and the air, the surface. So that's what the vadose zone is. And I think there was something else I could. Source zone is the source where it's released to the environment. So it could be a firefighting site. It could be an industry. It could be a lot of different places where the PFAS is actually released to the environment the first time. Well, actually, it could be not necessarily the first time. Okay, so a couple of questions. So would you characterize PFAS as floaters like petroleum compounds or sinkers like chlorinated solvents in the groundwater?
That's a fantastic question. And in general, I would say that they act like floaters because they do like to have their tails in the air. They like to be at that interface. And in surface waters in particular, the research is showing that you will have almost a concentrated layer at the very tippy top of, say, a surface water. And I've seen some indications that folks think maybe even in monitoring wells, the very upper layer is where you're going to have the highest concentrations. That said, just like petroleum and chlorinateds, once these are dissolved in the water, they're going to follow the water in an advective manner. So they won't really be floaters or sinkers at that point. as raw product, my understanding is that these materials are not typically denser than water.
Okay. Have PFAS has emissions from municipal wastewater? I mean, not municipal wastewater, municipal trash. Waste to energy facilities. Has that been evaluated? And is that a potential part of your diagram?
That it is. It is part of it. It is being evaluated. And there is a lot of discussion right now about what kinds of temperatures are needed to fully oxidize PFAS compounds. And up until very recently, my understanding was that if you were under about 1200 degrees, you were not going to fully mineralize PFAS. However, I've also seen some studies where folks have been doing thermal treatment of media, carbon, soils, and they seem to think that they're seeing effective breakdown so that you aren't discharging from the stack as low as 800 or 900 degrees. For right now, I think the jury is still a little bit out, but I do view treatment and incineration facilities as potential sources at this time.
Okay. Well, I think in the interest of time, we probably need to move on. I'll ask one more question. There's a whole bunch that came through, but some of them might get answered or addressed in the next presentation. But it's just in the diagram where you showed all the different, cycling around. Is that really substantially different than for a regular compound like a chlorinated solvent compound? Is there really a lot of difference?
Well, I think that there is in the fact that for two reasons. One is that the regulatory levels for these compounds in drinking water and in soil and surface water where they exist are very, very low. They're orders of, at least an order of magnitude less than your chlorinated type solvent. The other thing is chlorinated solvents, though pretty recalcitrant, do show evidence of biodegradation. And even the toughest chlorinated solvents can be degraded. So we haven't seen any evidence that degradation of perfluorinated compounds is occurring in any manner that is reflective of typical environmental conditions.
Okay, great. Well, thank you so much, Steve. There's also some people were even motivated to type in that they thought this was a really good presentation. So thank you again for presenting. I think we'll move on because some of these other questions are about retardation factors and soil and movement. So that is a big focus of what we're going to be hearing from next. So I'm going to switch over the presenter, and now I will introduce. So we've got three folks that are going to be presenting to us now. So I'll introduce all three, and then they'll start. So first, we're going to have Derek Sain. He is a senior research scientist with NCASI, which is the National Council for Air and Stream Improvement. For the past 15 years, Derek has conducted research and provided technical support to NCASI members who operate primarily within the forest products industry. Part of that work is focused on helping facilities find beneficial use options for their manufacturing residuals. Dr. Erica Houtz, I did it again. Houtz is a senior engineer at Arcadis, where she is the PFAS analytical lead and technical resource for PFAS site investigation and treatment and technology evaluation. She has been focused on PFAS for 10 years, so a lot longer than most of us, in both academic and professional experience investigating the environmental impacts of PFAS, and has significant experience in developing analytical and experimental methods for the measurement of PFAS in the environment and humans. You probably have seen her name associated with the TOP assay, the Total Organic Precursor assay analysis. So she is the originator of that TOP analysis. So she's also investigated and published on the fate and transport of PFAS in natural and engineered systems, with a particular emphasis on the fate of PFAS found in aqueous film-forming foams, so firefighting foams, at Arcadis. I think I already read that. Okay, so that's Erica. And then we've also got Chris Shepard. He is a principal hydrogeologist at Arcadis, and he's got 20 years of experience in environmental consulting. He's a licensed professional geologist, and his career has focused on environmental investigation, remediation, and quantitative hydrogeology. He currently serves as the team leader for the Vadose Zone Modeling and Mass Flux Focus Team for Arcadis's Technical Knowledge and Innovation, the TKI group. And they are going to be talking about a topic that comes up a lot for the states, which is sort of this soil, groundwater, and the transport between soil and water. And they're going to present on a report, study and report that they have recently published. So with that, take it away. Thanks.
So I'll start off, Jennifer. So yeah, as Jennifer just said, most of this presentation will be about the report that the Arcadis team put together, reviewing some of the models for evaluating PFAS and land-applied residuals and biosolids. Next slide, Chris. But so I'm just going to start off though and give a little bit of background and set the stage for that presentation. And as some background, before we even talk about PFAS, I'd like to just kind of focus in a little bit on the land application aspect of it, talk about why several industries practice land application as a management option for their wastewater treatment solids. And as you'll see here in the left column, they do that because there's a lot of benefits associated with it. And Steve alluded to some of these also, but applying the wastewater solids can be a source of slow release micronutrients. It can improve soil properties and texture, help increase soil carbon content, and then it can just be an attractive alternative to landfill disposal or shipping this material off into the landfills that are already filling up or close to filling up. So as we talk about the PFAS and land-applied residuals, I think it's important not to lose sight of all the benefits that come along with that land application. But now focusing specifically on PFAS, and as Steve also alluded to this earlier, is if you have a stream or an input of PFAS into your wastewater treatment system, some of those PFAS compounds will tend to associate with the organic solids in that system. And then as you remove those organic solids and apply them to the land for all the benefits I just mentioned, you now have a potential source of PFAS into the environment. And if you are a state and you were trying to evaluate what would be the impacts of those PFAS from those land applied residuals, one way to do that is through modeling. You can use fate and transport models to estimate the amount of leaching or surface runoff or migration in general from those land applied residuals. The problem is there is no standard modeling guidance or document available out there. And so essentially states are kind of left on their own to make these decisions and determine what is going to be the most appropriate model to use and what inputs should I use into those models. Next slide, Chris. And so just keeping with the background, I thought I'd focus a little bit on some of the activity here in the Northeast. One, because this is a NMOA webinar, so I thought we would give it a bit of a Northeastern focus. But two, really is a lot of the activity in this area has come out of the Northeastern region. The reason for that mostly is Maine was the first state to set screening levels for PFAS and land applied residuals. So a little over a year ago, they sent out a memo that set screening levels for 3 PFAS compounds. Now, after that memo was released, the Northeast Biosolids and Residual Association, or NEBRA, so they reviewed Maine's approach and they decided, there might be a better way to go about setting these screening levels. So NEBRA conducted a separate modeling effort to come up with a different set of screening levels for Maine. So that modeling was conducted by on behalf of NEBRA by Stone Environmental. So they are an environmental consulting firm also in the Northeast there. And they were using the US EPA pesticide root zone model, or PRISM, to come up with screening level estimates for what would be the PFAS concentrations in these land applied residuals, land applied biosolids. At what concentration would you still be protective of some of the groundwater targets in that state? In Maine, for those of you that are not familiar with that, Maine was using the 70 part per trillion combined PFOS and PFOA. And so after reviewing the NEBRA Stone work, it really just started to appear to NCASI that this PRISM approach that they took really was a valid solution to the problem at hand. And to us, all this activity, all the discussion that came out of this work in the Northeast, really one of the things that it started to highlight was the importance that both model selection and not only selecting the appropriate model, but the execution of that model in terms of what are the most significant parameters to focus on, what inputs have the most impact into your final results. And all of that just really started to factor into our decision to kind of prepare a report. And really because, as you'll hear about in the report presentation, there's just a lot of options out there in terms of which model to choose, which inputs, again, are the most critical to use. And without some guidance document to follow, it can be hard to sort of make those decisions and determine what path you need to take. And so in NCASI, we just saw a need for a resource that could just help states, other stakeholders, make more informed, more scientifically defensible choices when you're doing this type of modeling. And so in NCASI, along with some of our other partners within the municipal wastewater treatment industry, WEF and NACWA, AF&PA from the forest products industry. So we reached out and contracted with Arcadis to do a landscape review of some available models that could be used for fate and transport modeling of PFAS and land applied residuals. And so that's what you're going to hear about in this next section. But really, our hope is that with this report, it'll just be one of these first documents that gets reviewed before this type of work, the type of modeling gets conducted. Because I think as Steve already pointed out, as you'll hear from Chris and Erica, PFAS is a complicated compound, a complicated group of compounds. And a lot of critical thought, a lot of planning needs to go into the modeling. It's not that you can rely on some of the traditional or some of the other modeling approaches that have been used in the past. PFAS in a lot of ways is unique, so a lot more thought needs to go into it. And so that's what we're hoping this report will just help you out as a reference document going forward. And with that, I will pass it off to the Arcadis team.
Great, thanks, Derek. I think we'll just dive into the presentation that we're going to give on the work that we did reviewing the models and some of the considerations that went into selecting which models might be appropriate. So the first thing we did was assess the suitability of existing models for PFAS, and we were really focused on three major pathways that might be important to land applied residuals or land applied biosolids. We tend to use these terms residuals and biosolids interchangeably for those that are listening. So the first pathway that's quite important is leaching from soil to groundwater. The second is PFAS entrainment and runoff, either through soil particles or through a dissolved phase, and then the third being uptake of PFAS into plants. And so what we did not look into as part of this, just to say this up front, is some of the more minor transport pathways that we think are potentially applicable, but not very significant in terms of biosolid PFAS migration. And we didn't review surface water and groundwater models. We were focused more on the other top three. And then the final objective of the study was to share the findings through the dissemination of the report and then through presentations like these, so that others who are thinking about something similar, could have a sort of a baseline for how to consider which models might be appropriate and what those models might, a preliminary set might be. Next slide, please. So some of the challenges when it comes to selecting models that are most appropriate for predicting PFAS transport relative to biosolids are some of the things Steve already went over earlier. There's a lot of different kinds of compounds and they have unique characteristics. Now, certainly we can group some sets of compounds by either similar characteristics. For example, the sulfonates could be grouped together, or the carboxylates or the telemer sulfonates. And they could also be potentially more accurately grouped by their chain length, which is another feature that really controls their transport property. But because of this wide array of different chemical features that exist in these molecules, it's hard to kind of model them simply as a group, which is why, although there have been, kind of efforts to think about PFAS as a class, when it comes to thinking about their fate and transport, we do need to consider them at a minimum in sort of small groups or one by one. So no models to date have been specifically designed to model PFAS. Many of the models that are available are focused on metals migration or on very hydrophobic organic compounds, which is not what we're dealing with here. So we're dealing with compounds that have kind of unusual both oleophobic and hydrophobic features, but that are relatively mobile compared to a lot of the compounds that are, say, like on the Stockholm Convention. We do have a regulatory landscape that has been evolving quite rapidly. I think it's kind of stabilizing out in recent years, particularly as people are looking for more guidance from the federal EPA. I think there's been sort of a decline in individual state activity, but understanding kind of what the target concentrations that we would be concerned about are from like a regulatory point of view are obviously very important and informing, the output of the models. Next slide, please. So as I mentioned earlier, we were focused on 3 different main pathways of PFAS migration away from biosolids residuals. And again, we're worried about PFAS and biosolids because we don't see complete treatment in wastewater treatment plants. And really what we see is kind of a combination of things. We see quite a lot of the PFAS will just go out untreated with the effluent. We'll see a little bit of precursor transformation, particularly in treatment plants that have some type of biological treatment. And then we'll see some portion of the PFAS sorbed to the biosolids and then, leave as part of the residuals. And so the 3 main pathways are leaching of the residuals to groundwater, plant uptake of PFAS that are, in the soils or in the hydrated soils, and then runoff to potential, surface water features. We also have some secondary pathways that we don't want to dwell on, but we just want to indicate these are other pathways that could potentially be important, but in a more minor sense, potentially some air transport pathways of PFAS residuals, perhaps in the form of dust, and then other kind of interconnected transport pathways, so potentially deposition of PFAS that are associated with particles in air. And also another one worth mentioning is the secondary pathway of fish consumption of PFAS that are in surface water that may be partially there due to some type of transport pathway. But these are just sort of the secondary pathways that we did not consider important for the purposes of this study. Next slide, please. So the key PFAS parameters that we need to focus on when we're selecting the right models are going to be summarized in this table. And I think the most important parameter that has been demonstrated to date to be correlated with PFAS mobility is the organic carbon partitioning coefficient, sometimes called KOC. And this has high implications for leaching to groundwater, for surface water runoff, and for plant uptake. Generally speaking, we see this value increase as the perfluoroalkyl chain length increases. We do see some reversal of that trend in the really shorter chain length compounds. Additionally, we see typically that precursors that have the same chain length as like the carboxylate or sulfonate analog may exhibit a slightly higher KOC relative to the perfluorinated analog. Another key parameter that's important to modeling, really mainly to plants, is the soil to plant transfer factor. I suppose it can have a minor impact on leaching to groundwater in the sense that it may diminish the amount of PFAS available to leach to groundwater, but really this is mostly important in the context of plant uptake. One thing that's difficult to model at this point, but which can be sort of pseudo-modeled, is generation of PFAS from precursors. So we know we don't really have any loss mechanisms for the perfluoroalkyl acids, or we don't have any destruction mechanisms that can occur in the environment under natural conditions, but we can see potentially some generation of additional perfluoroalkyl acids from the precursor compounds. And this can occur in some of these matrices that might be relevant to leaching and surface water runoff. And additionally, we can see this occur within plants, within humans, within biological organisms. So we can see that sort of affecting our interpretation of plant uptake as well. Another partitioning or parameter that's important for PFAS modeling is this air-water interface partitioning. Because these compounds are by and large surfactants, particularly the ones that are on method 537 and similar lists, they have a tendency to assemble at the air-water interface. And we're not talking about volatilization, but we are talking about a mechanism by which these compounds can assemble a little bit more tightly in a space that can represent an additional sort of storage compartment. And so we do have some empirical values for this, although I would say there's not a lot of it available for compounds beyond PFAS and PFOA in the literature. But we think this has pretty significant implications for leaching to groundwater, because we think this is a pretty important retention mechanism. And additionally, it will also affect the amount of PFAS available for plant uptake. And then the final parameter that we think is important is, or rather the property, is electrostatic adsorption, which is usually sort of bound up in a KD value, which is also usually influenced by hydrophobic absorption. But this is where a negatively charged PFAS compound may absorb more strongly to positively charged soils than they would to neutral or negatively charged soils, and vice versa. So sort of an effect of ion exchange almost, where these compounds can stick to soils. And this will again affect how much leaching may occur to groundwater and how it may impact plant uptake as well. And then in terms of the surface water runoff, I think a lot of these parameters are influential just in the sense that they inform how much PFAS are going to stick to particles and will affect how much PFAS may be transported in surface water as associated with particles. So in terms of biosolids residual modeling, there are a number of considerations that are sort of PFAS specific. We've already discussed a number of those, and some really have more to do with how these things are land applied that are sort of PFAS independent. So what was the residual application rate? What is the terrain and climate? How much infiltration occurs in the soil? These are things that really affect the amount of PFAS that may leach. Certainly the type of plant and the plant tissue of interest is very influential on plant uptake of PFAS. We see that that leaves have sort of different partitioning properties than roots. So depending on the part of the plant that you're talking about actually can be very influential to where the PFAS actually ends up. And then other things like soil organic carbon content, the charge on the soil, how far the distance to groundwater is or the distance to surface water is. All of these things are pretty important. As we know, in really deep groundwater situations, even if we've had some type of a PFAS source, typically the concentrations are much lower because the migration to groundwater is just longer. And with that, I think Chris is going to take over.
Thanks, Erica. Thanks, everybody. I think y'all did a great job of sort of setting the stage for some of the complexity of PFAS and some of the things that challenges that we're dealing with and trying to select a model. The other challenge we really dealt with was which models do we use? There are a lot of models out there. So in this particular study, we wanted to make sure we didn't leave out any important models. We looked at US EPA websites, we looked at the USGS websites, we looked at other known compilation sites for models. And we identified over 70 models that could potentially be used to model the fate and transport of PFAS for these 3 primary pathways. Now, that's a lot of models, as you can imagine, and it would be quite difficult for us to do a thorough review of each of those models. So we added a step to the process where we screened out the models. So in this step, we looked at their model's general suitability to evaluate PFAS. You know, was that model designed for leaching and mine, for example? The other big question we had was, is that model maintained, or is that some sort of obsolete code that you have to run on some DOS emulator, and the developer of the code has long since retired, and it's very difficult to get your hands on. So those sorts of models we basically screened out from the beginning and said we're not going to review those models further. But in our report, you can see the comprehensive list of all the models we looked at. And on the next stage, what we did for the models that were retained, we did a more thorough review where we looked at their general capabilities of each of these models, and then their relative advantages and disadvantages. And in the coming slides I have here, we'll kind of talk about the models for each of the pathways. What I guess was unique about this is we weren't only isolating or focusing on models that can model all 3 pathways. We were looking at comprehensively at models maybe that just look at the leaching pathway, or maybe just look at the plant uptake pathway, and so on. So, and again, that's why we came up with so many models. So in approximate order of priority here, we'll talk about the leaching models first. We identified over 31 models that had been developed over, recent history. We screened out 13 of those models, retaining 18 models that we did a more detailed reviews. At the end, there were really 3 models that we felt bubbled up and would be more suitable for evaluating the complexities that we're dealing with when modeling PFAS. And those in alphabetic order here are Hydrogeochem, Hydrus, and SV Enviro. And I'm going to step back here. I'd like to point out that unfortunately only one of these models is free, and that's Hydrus, and that's the 1D version. The 2D, the 3D versions you do have to pay for, but also Hydrogeochem and SV Enviro are also software packages that you would have to license. But again, in our report, we do list out all of the models that we looked at, and a lot of the other models that were good and maybe perhaps better, more useful for screen level purposes. We talk a lot about those as well. So there were a couple characteristics I'd like to point out about the leaching models that we shortlisted here. They were all peer reviewed and well maintained. They all rely on Darcian advec flow as well as standard advection dispersion equations. They also accounted for parameters like the KOC and KD, so electrostatic absorption as well as the hydrophobic nature of the compounds. What they did not include, and at this time we didn't find any models, at least that are out in the public domain, that can model air-water interface partitioning in the vadosum. And the other thing that we're looking at, which we don't feel like is as important for modeling for residuals and biosolids, but certainly would be critical when you're modeling PFAS in areas or zones that have high concentrations of PFAS, where you can you get those concentration and surfactant effects, where that surfactant can actually reduce the pore pressure in the soils and can actually increase your flow. But again, from the residuals and biosolids perspective, we didn't feel that was important because of the concentrations that we're generally dealing with are well below those thresholds. The other thing that these models are capable of is evaluating soil heterogeneity, dual domain transport, which can be important, particularly in more complex environments. And also, all of these models have transient capabilities, so you're able to model transient sources and sinks. So, you know, these maybe frequent or infrequent land applications, precipitation, recharges, events, and so on. For the runoff models, we identified almost as many runoff models. There were a couple that overlapped with the leaching models. An example is actually PwC, and I'll talk about that in a minute. However, unlike the leaching model screening process, there were only 3 models that we ultimately retained for further review, and that was mostly because a lot of the surface water models had very specific objectives in mind that didn't really align well with the type of evaluations that we were looking at. So the one model that really bubbled up to the top during this evaluation was the pesticide and water calculator. That code also includes PRISM, and PRISM does allow for a leaching component. And you know what's nice about PwC model is you can actually look at all 3 transport pathways at once. So again, from a screening level tool, it can be used, although the name implies it's specifically designed for pesticides. It does allow the user to input chemical specific parameters, so you can essentially model some of the PFAS compounds with this model. And we thought that was acceptable. So some of the nature of PwC was it is maintained and peer reviewed, particularly for surface water components. It does allow, like I said, for the user to input site-specific parameters or chemical-specific parameters, either KOC or KD, depending on what you're dealing with. It does allow for multiple soil horizons and allows you to really kind of do a good mass balance of the situation. But this model is specifically designed for applications like residuals and biosolid applications or land applications in mind. The model gets used a lot in the pesticide industry to sort of screen out chemicals before they're allowed to be used in fields. So similar design in nature, and the outputs are specifically designed with some of the key outputs that regulators and the community stakeholders would have in mind for using a model like this. So, what is the end mass loading rate to a stream, or what's that concentration? Plant uptake models was quite a different beast. And I have to admit, as a hydrogeologist, this is not my area of extreme expertise, but we did have some folks on our team that this was their expertise. So I'm going to present some of these topics here to you today. But there were 12 models that we identified that could be used to evaluate PFAS uptake. And we did not go through a screening process with this because there were only 12. We did a more thorough review of that. And at the end of the study, we ultimately concluded that we weren't very pleased with any of these models, and I'll talk a little bit more about that. And so at this stage in the game, what we're recommending is that the community focus on the plant transfer factors, and I'll explain in just a minute a little bit more about that. So the issue we found is that most plant uptake models are designed for hydrophilic and lipophilic compounds, meaning that the model relies on the fact that these compounds will partition to carbons and fats, and it's primarily relies on that. But as Erica mentioned and as Stephen mentioned, these compounds are much more complex. They are generally ionized, and there are some additional properties that affect their fate in transport, particularly for plant uptake. So we also looked at some of those models are actually mechanistic models, and these generally are more complex models. And while some of those might be capable of acceptably modeling PFAS, at the end of the day, they still rely very heavily on PFAS and plant-specific transfer factors. And right now, the literature is, I would say, limited and in its ability to do that. So right now, it's very hard for users to do that. We did take the time when we were preparing this report to compile a lot of readily available literature, and that's provided as an appendix to our report that kind of shows the individual and plant-specific transfer factors. But again, because these mechanistic models rely on those, we felt like at this stage in the game, it was just better to rely directly on these plant transfer factors to evaluate plant uptake pathway. So there were a few key things that we observed when we were evaluating the plant uptake models and these transfer factors. That first, when speaking with regard to soil to plant transfer factors, and what I'm talking about here is if we measured PFAS concentrations in the soil, so you had some sort of compound that's, you know, maybe partially in the dissolve phase in the pore water and partially bound to the soils. That's what I'm talking about with regard to soil to plant transfer factors, that we generally see a decrease with increasing PFAS carbon chain length. Now, that aligns pretty well with what everyone's been saying here is that because these PFAS compounds, bind to the soils more strongly, that generally the plant absorbs less of it for these longer chain compounds. What we also saw is that the transfer factors were lower for the PFSAs and than they were for the PFCAs. Now, if you can recall, and you probably don't if you're like me, that the PFSA, an example of that is PFOS. So that's one of the high priority contaminants that we're dealing with, and an example of a PFCA is PFOA. So that's why we wanted to kind of specifically mention those here. So the other studies that were out there also looked at solution to plant transfer factors. And what I mean by solution to plant is really like, you could almost think of it like a garden where, you know, I have it in my house, I'm forgetting the word, but basically that the roots are in the water, or it's mostly the pore water in the soil, and you're measuring the pore water concentration and then comparing that back to the plant uptake factor concentration. And what we saw in the compiled studies is that fruit transfer factors were generally decreased with increasing chain length. So that's pretty similar to what we saw with the soil to plant transfer factors. But conversely, for the root transfer factors, so this is here I'm talking about the PFAS compounds that bind with the roots themselves, that the transfer factors actually increased with increasing carbon chain lengths. And that might be because the roots are sort of bound up into the soils, and so and there's just more surface area for that PFAS to sort of absorb to on the exterior of the root. And again, that's not my expertise. You can read more about that in our report. And then finally, the last thing I'd like to mention real quick is that fruit transfer factors were lower than the root transfer factors. And again, just based on some of the concepts I was talking about here and some of the chemistry presented above, that kind of intuitively makes a little bit of sense there. So I'd like to take almost like pause and take a step back. So we talked a little bit about models. We identified over 70 models, and there's a good reason we found 70 models out there, and that's because a lot of people and groups felt like there was a need for a specific model out there, and each of these models is going to have its specific design or focus, intended purpose, and strengths and weaknesses. So it's important to consider those. So again, like you may not need a really complicated model to evaluate PFAS. So you need to consider the goals and the purpose of your study and modeling assessment. Are we doing more of a screening level assessment? In which case, can you use a more conservative model like PwC to evaluate all three pathways, taking into account some of the information that we presented here? Or does it make sense to do a more detailed or more site-specific model where you can account for more of those complexities that we're dealing with PFAS? And in which case, we would recommend using a combination of models like PwC for the runoff, plant transfer factors from literature, as well as HYDRIS. And I just mentioned HYDRIS because it's the free leaching model here. So Again, there are a lot of factors that go into model selection, and you've always got to make sort of your own determination here. That was not really our goal of this project, is to tell you this is exactly what you need to do, but rather to provide you with the information, hopefully to make a better decision on selecting the model. So to kind of conclude, what we found in our study is, and that's been reiterated here several times, is that PFAS chemistry is unique, and that unique chemistry has significant impacts on its fate and transport, particularly compared to a lot of the other contaminants of concern that we deal with, that we're, as a regulatory community, that we're used to dealing with, that have been mentioned, like gasoline hydrocarbons or chlorinated solvents or metals. Another important factor is we did not find any models that were specifically designed with PFAS in mind, and nor did we find any model that could handle all of the parameters that we thought were important to evaluating the more accurate fate and transport of PFAS in the environment. And kind of lastly, I'd like to talk about that some models are more suitable, and those are the ones we tried to identify in our report. But at the end of the day, again, you've got to consider the important factors like retardation, precursor transformation, transfer factors, mass balance. And what I mean by mass balance is, PFAS compounds the same PFAS molecule can't go up into a plant and into surface water and into groundwater. So if you look at those models individually, you need to make some careful assumptions and perhaps run these models iteratively to manage that mass balance. Now, if only a tiny fraction of that PFAS is going to a specific pathway, for example, maybe there is negligible runoff at a site, or there really aren't any plants at a site, you could ignore that pathway essentially. The other thing that we did notice, and I don't think was a big surprise, is since this is such an emerging contaminant and there is a lot of research out there, and this compound is complex, or this class of compounds are quite complex, is that there are still a lot of needs, future needs that we see potentially for research or model evaluation, looking at the ability of these models to predict PFAS and fate and transport. As I mentioned, looking at the mass balance and losses via the three pathways from the leaching side of things, looking into air-water interface partitioning and surface tension effects, and also evaluating perhaps some of the non-linear behavior. And what I mean by that is we often assume that chemicals sorb and desorb at the same rate. Studies are indicating that that's not true, that it can take, as Stephen mentioned, a lot longer for these chemicals to flush out than you might otherwise think, given, classical sort of fate and transport chemistry concepts. And then for runoff, what we'd like to look into are better understanding some of those desorption mechanisms, particularly for, air-water interface partitioning. Generally, we felt that was pretty negligible for most of these models, but it could still be important in unique circumstances. So that would be another place that we'd like to see a little more research done. And then finally, for plant uptake, I'm kind of maybe going to start with one I feel like is more important, and that would be, ultimately having a more comprehensive compilation of plant transfer factors. Right now, it's very difficult for the community to come up with these, having to scour research papers and universities for some of these things. And again, we did try to compile those, but at the end of the day, we would love to see some sort of big database of these. And then on top of that, there needs to be, I would say, more robust studies. And some of these studies didn't look at linear regression evaluations to have a better understanding of concentration and other factors that could affect uptake. So they were, soil, just comparing one soil sample, for example, to one plant sample. So those evaluations could definitely be more robust, and then ultimately having that information integrated into existing plant uptake models. With all that said, it was a lot of information that we shared with everyone today. Thank you for staying awake. I'd like to tell you that all of this information is available that we presented today in the Arcadis report and a report on NCAST's website. It's available. We provided a link here. You should be able to Google and find it, but I did find it's much easier to actually use the hyperlink to find it. And Derek could probably help you navigate a little better than I could there. The other thing I'd like to point out is just a big thank you to our Dr. Houts for helping with this report and our numerous team members that made it possible, and obviously NCASI and all their partners who really supported us and guided us through this evaluation. So thank you very much, and I'll pass the reins back to Jennifer.
Excellent. Well, thank you so much, Chris and Erica and Derek, for the information and the information about the report. So I will just remind everybody that I will be posting these presentations on the NMOA website, so you will be able to get them. So we have a ton of questions, but I think I'll just, in the interest of time, we just probably do a couple. But so states and governments are very interested in trying to develop standard, guidelines or screening numbers or guidance regulatory numbers for protection of groundwater for soil, so soil numbers. So can you use those models that you came up with at the beginning, those three? Would they be appropriate for that, or what do you advise governments to be using?
It's a challenging question, and I'm not going to give you one straightforward answer, unfortunately, but I think it depends again on how complex the situation is, and if you're trying to develop one single screening level that represents the entire state, or if the state deals with it by region or different environments, that would certainly affect the factors. I know states and Stone Environmental have used PwC successfully in the past, so that might be one option. It will tend to be a little bit conservative compared to the other leaching models. And again, it also depends on the pathway. Are you establishing your screening levels for only the leaching and groundwater pathway? Or are you trying to account for all three pathways? So there are a lot of factors there, and that's why I can't give you one answer. But again, it's difficult, but that was the other part of this report, is we wanted to really get people thinking about that, and it's going to be a real challenge. And I don't know, Derek, if you had anything to add there.
No, I think that was a good response, and I think it's important, the slide you had about model selection, all those things you mentioned really kind of play into it. And as you said, are you trying to do a statewide analysis, or is it more site specific? What are the time and monetary constraints associated with it? So, a lot of it's going to play into which kind of model and which approach you pick.
Okay, another question is about field verification. Was there any of that done, looking at what's predicted by the model versus what you find at a real site with real data?
To my knowledge, there's been very little done on that to this date. Again, it is so complex that if you're really trying to model it accurately, there have been several lab studies. I know University of Arizona has done a few where they're looking at that, but they're still trying to adjust these models to account for several of these factors. And I think until we have adequately accounted for those factors, your calibration is always going to be off. So that's where the users are going to have to keep in mind how they're using the model. So the input parameters and assumptions that go into the model are going to be critical. At this stage in the game, it's probably going to be recommended to make some somewhat conservative assumptions where you have unknown factors. They have started, like Erica mentioned, establishing air-water interface partitioning coefficients, but I did mention that to date, there are no models in the public domain that are able to do that. I believe there are one or two in the research community at the universities where they are working on those models. But unfortunately, at this stage in the game, field verification, while it would be very useful and helpful, and that was one of the things I was trying to point out, will also be very difficult because our models don't sort of lack perhaps adequate sophistication to accurately model PFAS behavior, particularly in the vadose zone, and particularly for more complex or deep vadose zones where soil moisture content varies quite a bit over time.
Okay, and then I guess probably one last question is about just, this is sort of what's about biosolids, but states are also interested in paper mill sludge and that sort of land application as well. So are there differences? Can you say anything about similarities, differences, PFAS content testing, modeling, anything?
If I could chime in on this one, I mean, I think we would suggest the same models would be used, even though we were routinely referring to biosolids. Like I had said at one point, we're kind of using that interchangeably with other kinds of residuals. But the webinar that you guys gave last week, there was some data presented by, I think it was the state of Maine, and they had surveyed 8 or 9 paper mills for PFAS in their residuals, and they had come up with really low levels. I believe all of the residuals were under the main screening level for biosolids. So that's one potential resource to understand data. I mean, my understanding is that sometimes we do see quite high PFAS concentrations in paper residuals, but I suppose it depends on the specifics of the operations at that facility. Like I know, for instance, we have a site in Germany where we've seen relatively high PFAS concentrations in residuals, but not necessarily PFAS, PFOA, perhaps some of the precursors.
Yeah, and I would just say those two materials in a lot of ways share a lot of similar properties. But if you are familiar with paper mill residuals versus biosolids, I mean, there can be some differences there too. But I think, as Erica said, probably a lot of these models should be able to handle those kind of material-specific inputs into the models.
Okay, yeah, I'll just add one observation with the paper mills as well. I think sometimes if they're using recycled paper as an input, that can be a factor in PFAS levels. So,
certainly, the concentrations of PFAS, yes, and then within pulp and paper, there's also primary versus secondary and the types of properties associated with those materials as well. But yeah.
Okay, and I guess we're a couple minutes past 3, so sorry, folks, if you need to get off. But can you just talk a little bit more about the root uptake and the leaf, and I guess it depends on what kind of vegetable or food that you're growing as to where the concern is, I guess, for.
At this stage, I'd refer them to the report. Again, the report does provide some more information, and I think that was perhaps a little bit beyond the scope of our report, but I do know that we did speak a little bit more to that in the report, but I don't recall all the specifics. But again, like I think, root transfer factors were higher than fruit transfer factors, and obviously it would depend on the plant as well as the PFAS that you're dealing with. And I think there is a little bit of a compendium table at the end of our report that does discuss which plants were evaluated and what those specific transfer factors were.
Okay, and then I'm going to ask one more question because it's pretty specific, and then we'll sign off here. So has Arcadis published a compilation of physiochemical constants for PFAS, or is there a publication anywhere?
So several people within Arcadis put out a book last year called the Emerging Contaminants Handbook. I believe there is a compendium of constants in that handbook. That is something that you have to pay for. We worked on something in 2016 through the name is escaping me. Another Arcadis author document that has a big compendium of physical chemical parameters. And then I think I would certainly be remiss not to plug the ITRC tech reg document and the fact sheets that also have quite a lot of physical chemical property information available that's publicly available.
Okay, and then I'm going to make one last comment that came in here at the end. So the presentation that will be June 23rd, it's lessons learned on sampling and cross-contamination, but one of the presenters is from the biosolids, the residuals program in New Hampshire, and he will be talking about some of this a little bit more in his presentation as well. So for people that are interested in biosolids and residuals, try to tune in for that webinar as well. So with that, I think thank you so much to everybody that joined us today. Thank you so much to the presenters. Those were great presentations and a lot of good information. And the presentations will get posted, and each presenter has their contact information in the presentation. So you'll be able to follow up there. So with that, thank you again so much to Steve LaRosa, to Derek Thane, Erica Houts, and Chris Shepard. Thank you, everybody. And we'll sign off. Bye-bye.
Thanks. Bye.
Thank you.
Thanks. Bye.
Take care.